Okay, so okay, so we're going to do more counting. Okay, so first rule of counting is objects from a sequence of choices and I possibilities for the. You construct the objects. You write down a procedure to construct your objects, and what you do is, for example, for the 2 bits for bit strings, for each bit you decide whether it's a 0 and 1. And then for the next one, you decide whether it's 0 and 1, and you get 2 times 2 times 2 times 2, whatever number of bits you have. Okay? And for other objects, you do this in a different way. You can get a poker hand with a joker by first picking one of the 2 jokers, and then that's 2, and then picking a 5-card hand, which is 52 choose 5. So therefore, I'm kind of using it recursively, right? To get the 52 choose 5, I had a way to do that as well. Okay? So once you build up these ways to count, you can sort of piece them together. Okay, second rule of counting, if order doesn't matter, you count with order, and then you divide by the number of orderings for each sorted object. Now that doesn't always work, but it works in the notion of finding subsets. If you want a subset of k items out of n, a subset of k items from n from a bigger set of n, you're trying to you just care about which subset you have. So for poker hands, you just care about which hand you have. You don't care about the order you got the cards. Okay, so that in that case you can just divide out the order. Okay, inclusion, exclusion. If you have 2 sets of that object, what you do is you add the number of each, then you subtract the intersection of the sets, because what you do in inclusion, exclusion, again, we try to get to the ideas in this, right? You should be thinking about why is this true? Always why is this true, right? So you have 2 sets, you added up all the size of the 2 sets. Now, the problem there is that one element may have been in both sets, which means you've added it twice. You've added its size twice. So what you would like to do is you need to subtract that number once to get rid of it. And now you've counted it once. Okay? If it's disjoint, you just add. If the sets happen to be disjoint, there are no elements in common, so the subtraction doesn't need to happen. You can do it if you want, because the intersection is 0. So it's just a special case. Okay? So here's a simple exclusion, exclusion. This is a proof again. Again, you should always think of why things are true. Fermat's little theorem. Why is it true? Right? Always, in some sense. If it's not very far in this course to go back and see why things are true. And doing that exercise will help you get the kind of thinking you need to do well in computer science. Okay? So in T, in S, now you see this, the elements in this intersection are counted twice, so we subtract. Okay? So that's the proof. Okay, so size of, if you want to count S union T, where the size of S, where there's sets, then you just use this formula. You take the size of S plus the size of T and subtract the intersection, the size of the intersection. Okay, we can do this 3 ways. It looks a little bit worse, right? Okay, so the first term is you just add all of them, but you see here that these 2 are added too many times, right? When you add these, you add elements in here, you've added them once for this size, and you added them once for this side. Okay? So what we do now is we subtract out this one. We've added these elements at least twice, so we subtract them out. And then we've added these elements twice or more, in fact, and we subtract them out. And then we add this element twice, so we subtract it out, right? So we're subtracting it out. And then finally, what we've done here is we have to add this back. Okay? What we've done is we've added this, so for each element, we counted it here, we counted it here, and we counted it here. So we overcounted all the ones here twice, and these twice, and this twice. And when we do this first addition, we've overcounted this middle part 3 times, because it was in every set. Okay, but now, once you subtract out these things, these pairs, you've subtracted all of these once, so that these guys are correct now. You subtracted this one once, right? And you subtracted this one once. So all those are correct, but these guys, what you've done is you've added them 3 times, and then you've subtracted them 3 times. So you don't have any numbers. You're off on those. You haven't counted them once. You want to count everything once. So then you add it back. Okay? Okay, in general, it looks like that. Oh my. But it's just the same thing. It's sort of, the proof is a little scary, but it's just scary. Okay, but that's fine. Here's what it is. You want to take the subset of A1 through AN. Before we did 2, and then we did 3. Now we're going to do an arbitrary number of sets, the union of them. And what we do is the first term is just adding up all the sizes of the sets. The second term is subtracting all the intersections. And the third term is adding all the three-way intersections. And the fourth term is subtracting all the four-way intersections. Okay, and so on. Now, why is this true? Let's think about an element. So again, before we were asking, how often is an element counted? Right? That's what we were looking at. How often should an element be counted? In the end, after you add and subtract and add and subtract, how many times should you count each element in the union? Once, right? So what we need to do is see how often each one is counted, and then we need to confirm that it's once, right? That's what we need to do. How often is X counted? Okay, well, here, if X is in K sets, okay? It's in K sets, yes. Intersections. Oh, shit. Yeah, sorry, a new slide. Cap and cup are very different. Okay. Oh, that you don't need to see. Okay. So, what's going on? Okay, look. Well, you can just pretend I'm writing on the board. That's what everybody else does. Okay, so cap. Okay, cup. Oh, yes. Wait, it is cap. Oh, yeah, next one. Okay. Where is it? Okay. Oh, I only have... Sorry. Cap. Okay. Sorry. Okay, so let's see if it works. Okay, good. Oh, maybe it works. Okay, good. Okay, so intersections, right? So then an element is in the intersection of these K sets, right? Meaning it's in all of them, right? That's what it means to be in an intersection. You're in every set. Okay, so in this first term, when you add these the sizes of these A sub i's, what do you get? You get that you've counted this element K times, right? In that very first summation, right? Because it's in all of those sets. And now in the second summation, it's in K sets here, and in that summation, you're going to choose 2 of these K sets at some point in this summation, right? And if you choose any 2 of these K sets, that element will be in the intersection because it's in both the sets. So it's also in any 2 of them, right? So it's going to be counted in that summation K choose 2 times. For every pair of the K sets, it will be counted in that summation as part of that size. Okay? And that's what the minus K choose 2 is. And then the third one you're going to add plus K choose 3 because out of these K sets, any 3 of them will appear in the third summation. And so therefore that element would be counted K choose 3 times. Okay? Okay, and that's in the intersection of any 3 sets that are a subset of this. So is this 1? Is this 1? This needs to be 1, right? We need to be able to say this is 1 for us to have counted at the right time. Yes. Okay, it's 1. Okay, let's go on though. Okay, so, okay, here's the proof. Well, 0 equals 1 minus 1 to the k. And this is the binomial theorem, right? I'm just expanding out this expression, right? So the first term is 1 to the k, which is 1. The second term is 1 to the k times minus 1 to the 1, right? The 1 to the k minus 1, and so on. So this is just the expansion of this term. If you don't get it here, I'm going to do it again, so it's fine. But this is just a binomial expansion of this term, right? And that equals 0. right? So this whole thing equals 0. Okay, so then you just solve and you get 1, and you subtract the other side, and you see that this is the same thing. Not a super instructive proof, but it is exactly doing what we said, right? It's adding and subtracting until we get 1. Okay? So that's the proof of the general theorem. Okay, let's use inclusion exclusion. So how many permutations are there of 1 to n? How many permutations? N factorial, exclamation point. Well, but there's no x there, so it is n factorial, right? Why is that? N ways to choose the first element out of all the guys, n minus 1 ways to choose the second one. See what I'm saying? Just go one more step. Don't just remember it. Just say it to yourself while you're learning, right? This is what you need to do. Okay? N minus 2 to do the third one. So where permutations where no item is in its proper place, or no item is a fixed point. Okay, so let me just go through this definition with an example. Okay? Is that a derangement? It's a permutation where it's a derangement. That's what the title is. Okay, is there no element that's where it belongs? Is that a derangement? Where does 1 belong? 1 belongs in the first place, right? And 2 belongs in the second place. And 3 belongs in the third place. So is this a derangement? No, right? Because all of them are where they belong. So this permutation has the property that everybody is where they, in the position they sort of started in, right? Does that make sense? It's called a fixed point of the permutation. It's called a fixed point because remember, permutations are 1-to-1 functions. So that's why it's called a fixed point. This permutation maps 1 to 1, and 2 to 2, and 3 to 3. Okay? How about this one? Does that have any fixed points? Yes. I asked, is that a derangement? No. Does it have fixed points? Yes. Okay. 3 is a fixed point. Right? How about that one? Does that have any fixed points? Well, 3 is not where it's not at the end. 1 is not there. So that is a derangement because it has no fixed points. That's a derangement. Are there any more? Any more here? No. Okay. There's no more because I just wrote 1, 3, 2 and 3, 2, 1. Those are all the 6 possibilities, right? Because the total number of permutations is 3 factorial, which is 6. So I wrote them all down and I just checked them. Does that make sense? So there's 2 of them. Okay? Okay, how many are there? There's 2, right? So let's see how we count them. In this case, we know what we just wrote down all the possibilities, but let's count them using inclusion exclusion. Okay? Okay, so what we're going to do is instead we're going to count the opposite. Instead of counting the number of derangements, we're going to count the number of not derangements because those are a little easier to work with. Okay? A not derangement is all the permutations where I is a fixed point. Okay? So it's a set of permutations where the item I is in the ith position. Does that make sense? Is there any questions on this? Okay. So AI intersect AJ are the permutations where both I is mapped to itself, I is in the ith position, and J is in the jth position. Okay? It's both of these properties are holding. Okay? So now, so this is what the number is, right? So here we have, there's 3 choose 1. This is just a sum over the 3 A sub i's. And now what we have is, once we fix 1 as a fixed point, how many permutations are there? If I say the first guy goes to number 1, how many permutations are there? 2 factorial, right? There's 2 other ones. Either, say I fix the first position to be 1, then I could have either the other 2 positions be 2, 3, or 3, 2, right? It's 2 factorial. Okay? And so on. Then I can say, if I fix 2 of them, there's really only 1 permutation. left, right? Because if I fix 1 to be 1 and 2 to be 2, 3 has to go to the third spot. Or if I fix 1 to 1 and 3 to 3, 2 has to go to the middle spot, right? And so on. And there's only one permutation where they're all three the same. Okay, so I just did inclusion, exclusion. I did the sum of the AIs, A1, A2, and A3. And then I said the sum of A1 intersects A2 minus A1 intersects A3, and so on. Okay? And then I counted them. Okay? So there's 4. But I thought there were supposed to be 2. Wait. Why is there 4 instead of 2? What did I actually count? Did I count the number of derangements or the number of permutations that are not derangements? Yeah, I counted the number of things that do have a fixed point. Okay? So I'm trying to find all of the things, so I do n factorial minus this number. So I get 2. I get the same answer as if I enumerated. Okay? Okay, so you can do this for fun. This is a little scary, but we can do it. For n items, there's n choose 1. There's n choose 1, right? How many different? There's n possible fixed points, right? And you're picking one of them. Okay, so you're saying that you fix, say, for example, one of them could be that you mapped first item to itself. So 1 goes to 1. And now how many permutations are there? Now all the n minus 1 others can be permuted in an arbitrary way. So it's n minus 1 factorial. Okay? So the size of a sub 1 is n minus 1 factorial. The size of a sub 2 is n minus 1 factorial, right? Once we fix the second item to go back to where it belongs, then all the other items can be permuted arbitrarily, and there's n minus 1 of them. So that's n minus 1 factorial. Okay? Now the second term is the same thing. Now what I'm doing is I'm picking 2 places to be fixed points. So let's say, for example, I fix 1 and I fix 2. Okay? So now there's n minus 2 items, and they can be in any order. Okay? There's n minus 2 items, and they can go in any order. So that's n minus 2 factorial, and so on. Okay? So this is the formula. Okay? So the number of that's the number of not derangements, right? We did this. This is a standard trick in counting. Sometimes it's easier to count the opposite of something. Instead of a set, you count its complement in your universe. Okay, so the number of derangements is this n factorial minus this number, so that the signs are a little off. Okay, so then term I is equal to this. Okay, n factorial, I'm just expanding out the n factorial, and then minus I factorial. So that cancels, and you get n factorial over I factorial over negative 1 to the I, times negative 1 to the I. So that's what these terms look like. So this is what it says. It says the number of derangements is n factorial times this series. Okay? So it's kind of nice in the end. It's not so bad, right? It's not so ugly when you put it in a sum. And in fact, that series has a meaning. Does anybody recognize a series? When somebody says you recognize a series, it should be either 1 over 1 minus x or e to the x. So which one is this? It's e to the negative 1, right? Right. So it's e to the negative 1 as n goes to infinity. So it tells you something kind of interesting. 1 over e of the permutations are derangements. Okay? That's kind of cool, right? E is the base of the natural log. Okay, don't worry too much. It's a little bit, it's just a little bit messy, but it's not so bad, right? It's sort of a nice use of inclusion exclusion. Okay. But you're going to see this another way where it's not so messy later when Babak does probability. So you'll see these objects again. So I just wanted to use an example that you'll see again. Okay. So now let's talk about sampling k out of n items. Without replacement, where order matters, it's n times n minus 1 times n minus 2. Now sampling k out of n items is another way of just saying I'm choosing k from choosing a subset of size k from n items. Okay? So that's just, it's just phrasing. I'm just telling you different phrasings for the same thing. Okay? So when order does not matter, you can just, in this case, since all the items are kind of different, you know the number of orderings that correspond to the item, so you just divide out by factorial, right? K factorial, all the possible orderings, and you get this expression, and we call that n choose k. Now with replacement, if order matters, it's the number of choices. Now I'm picking items from a set of n items, and then I can pick the same item again. Okay, so I could pick students. There could be 30 students out of 800 that are in the course here. But I could pick a random one, and then I pick a random one. I get to pick them again. Okay? That's what with replacement means. But I care who got picked first. It's a line. Okay? So the first choice is n times n, all the way times n, right? So it's n to the k. And now when order does not matter, what do you do? Okay? Use a second rule, maybe. I guess you want to divide out the orderings, right? But that sort of depends on how many of each item we choose, right? Different number of unordered elements map to each ordered element. Let's just say ordered. Okay, so let's think about this unordered element. 1, 2, 3. There's three factorial. The way I'm writing unordered elements is I'm just going to write them in order. It's kind of ironic. Okay, so I just put it in a fixed order, a canonical ordering, and say this represents the unordered element, right? Because I don't want to write them differently. Ace, king, queen, are they just going to be? Actually, the unordered element is listed in order, right? So just to make it singular. Okay, there's only one ordering like this. Okay, so there's three factorial elements that map to it. But I could pick out of my set 1, 2, and 2. Right? How many different orderings of 1, 2, and 2 are there? Are there 3 factorial? No, there's 3 factorial, but then you have to divide out the 2, remember? Remember the second rule? Now you can use the second rule of counting to count the number of ordered elements that map to this, right? There's 3 factorial orderings of 1, 2, and 2 if they're distinguishable, but you can't tell the difference between these 2's, so you have to divide out by the orderings of the 2's. 2 factorial. Okay? And in fact, we could have picked the same item 3 times, and there's only really one ordering of that. So you don't divide. You can't divide evenly. So how do we deal with this mess, right? It's a real mess now, right? It's really a disaster. Okay? It breaks our previous rules completely. Okay, so we're going to do something a little different. Okay, so for each of $5, we're going to pick Bob or Alice. Okay, and so now, how many ways can we pick $1 to go to Bob and Alice? Well, it's either Bob or Alice. So there's 2 choices for the first $1, 2 choices for the second $1, 2 choices for the third $1, and 2 choices for the fifth $1, right? So that's 2 to the 5th possibilities, right? So we can count that. We can count all the ways to distribute the dollars with order to Bob and Alice, and there's 2 to the 5th of those. Okay? But how do we divide out the order? Let's see if we can divide out the order. So the thing is, these dollars are, I don't care which dollar I have. $1 is $1, right? It doesn't matter whether I got it first or last. Okay? So one ordered set, right? So this is the problem here. One ordered set for, say, Bob got all the money, and there's one ordered set, Bob, 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 and Bob again, and Bob again. Okay? And now there could be another one, and there's only one ordered set that corresponds to that. Here, these are different orderings. When Alice gets $1, there's already there's 5. So we can specify this, right? It's just a mess, right? So in some sense, this graph I had last time, where I took the ordered objects here and the unordered objects here, these degrees are all different. So it's a real mess. Okay? And this is the same kind of problem, right? What we're doing is we're picking either Bob or Alice with replacement 5 times. Essentially. For each $1, we're picking either Bob or Alice. Okay? So, it's just, this is the sorted way. These are the ordered items. These are unordered items. And these are the ordered items where A, B, B, B is different than A, B, A, B, B. For us, we think of them as the same. And then $2 went to Alice and 3 went to Bob. So the second rule of counting doesn't work at all, even in this example, for 5 and 2, right? Okay, so let's try to do this. Let's try to count the number of ways. How many ways can they split their dollars, right? Okay, so now we're going to have 3 people, Bob, Alice, and Eve, to make this a little bit more interesting. Okay, so what we're going to do is Alex gets 3, Bob gets 1, and Eve gets 1. So we could write it like this: A, B, and A. So that's sort of, it's a nice way to write it. Alice's dollars are all together, Bob's are together, Eve's are together. Okay, so now, how do we describe these patterns? Okay, this is a pattern. And now, if Alice gets 3 and Bob gets 1 and Eve gets 1, this is the pattern. There's only one pattern here that corresponds to Alice getting 3, Bob getting 1, and Eve getting 1. So now we just need to count the number of these patterns. Okay? Does that make sense? There's a one-to-one mapping between a split of money between Alice, Bob, and Eve and these patterns. Okay? So all I need to do is count the number of these patterns. Okay? So here there's commas and parentheses, but let's see how we might specify a pattern. So one way to specify a pattern is see when does Alice's dollars stop? Like figure out when that happens. Okay? And then figure out when Bob's dollars stop. And then figure out when Eve's dollars stop. We know when Eve's dollars stop. When does Eve's dollars stop? At the end of 5. Okay? So we sort of reorganize everything, assuming the first 3 go to whatever Alice gets, she gets them first. And then Bob gets his. And then Eve gets hers. Eve gets the rest, right? Once Alice and Bob get theirs, Eve just gets what's left, right? That's another way of thinking about this pattern. Okay, so what we're going to do is we're going to think of the $5 as stars. Those are things we're handing out to Alice, Bob, and Eve. And what we're going to do is we're going to split these stars into 3 groups. And the way I'm going to split these stars is I'm going to just slice it. Okay, for this pattern, I would slice it after the first 3 stars. I put in a cut there, or what I'm going to call a bar, and put a bar there. And after Bob gets 1, I put a bar there, and Eve gets the rest. Okay? So what I'm going to do is, for this pattern, with Alice got 2, Bob got 1, and Eve got 2. So I'm going to say after the first 2 stars, I put one of these bars down. And that tells me that Eve got 2. And then from Bob gets 1, so I move over 1 star, and I put another bar down. Okay? And then there's 2 more stars. Okay, how many stars are there? There's 5, corresponding to dollars. How many bars are there? There's 2. There's 1 less than the number of people. Because once I put down Alice's Bob, the bar for Alice, I have a bar for Alice, and I have a bar for Bob, and Eve doesn't need a bar because that's just the rest of the stars. Okay, so here, let's write the pattern for this one. This is the pattern we want. We want to split up $5 among 3 people. Alice gets 0, Bob gets 1, Eve gets 4. So add them together. That's 5. This is one of the things we're trying to count. This is what the stars look like. The stars and bar diagram. Okay, so first I say Alice gets 0. So I put the bar in this position, and no stars are before this bar. So Alice got 0. Now Bob gets 1, so I move the bar over by 1, and Bob gets 1, and Eve gets the rest. Okay? So each of these splits of dollars corresponds exactly to a single diagram of stars and bars. Okay? Again, it's 1-to-1. Okay? So each sequence of star to bars is a split. It's 1-to-1. It's backwards. If I give you the stars and bars, you can tell me how many dollars Alice, Bob, and Eve got. If you tell me how many dollars Alice, Bob, and Eve got, I can tell you, I can write down the star and bar pair. It's a 1-to-1 mapping. I have an inverse function and a function forward. Okay. So this is a real big counting. If I have a 1-to-1 mapping between two sets, they have the same size. So now all I need to do is figure out how to count the number of these star and bar diagrams. Okay? Okay. That's what we need to do. So again, I started with sampling with replacement, and order doesn't matter. And then I moved it to this problem of I have some number of dollars, say N, and I want to split them among some number of people, say K. Okay? Yeah. Or actually, I might use K and N the other way. Okay. But, okay, so how many different 5-star and 2-bar diagrams? Okay, so that's the star and bar diagram. Let's see what it looks like, right? It has 7 positions, right? This one has 7 positions, in which in any position we could either place a star or a bar. Yeah. Yeah. Yeah, it's easy to believe there should be 8, but there's 7. Okay? Okay, I always have this argument with people, or this disagreement. Yeah, okay, but it's 7, right? Do you see that? 1, 2, 3, let's see what Arjun was doing. 1, 2, 3, 4, 5, 6, 7, right? 5 stars and 2 bars. That's also 7. 5 plus 2. Okay. Okay, so 7 positions, and all we have to do, if we place 2 bars somewhere in there, where will the stars go? Everywhere else, right? So this is, again, it's this. Bars in the first and third position, right? That's what it's saying. How do I specify this? I could just specify it by where the bars are. Okay? Here the bars are in the second and the 7th position, right? Okay? So how many ways are there to choose where the bars are? Well, 7 choose 2, right? There's 7 positions, and I want to choose 2 of them. That's it. Okay, so we know how to count that. And there's 7 ways. Now we know how to count the star bar diagrams, so therefore we know how to count the number of ways to split $5 among these 3 people, and we also can count the number of ways to take a sample of 5 objects from 5 objects from 3 people. Yeah. Yeah, it gets to be, it doesn't turn out to be 1-to-1 if you're not very careful. Yeah. No, I understand what you're saying. What he wants to do is start with 5 stars and figure out where to put the bars. But sometimes you can put 2 bars in between the 2 same person, and then it becomes you overcount, right? So you got to be careful with that, right? You're going to overcount here, right? Right. Okay. So it's really a way to sum up n numbers to sum to k, right? We have $5, that's k, and we had 3 people. How much money did Alice get? How much money did Bob get? And how much money did Eve get? Okay, so this is the same thing as the Alice, Eve, and Bob problem. Okay, where k is 5 and n is 3. Okay, so it's also k from n with replacement where order doesn't matter. So again, it's like, say I'm picking a subset of all of you. Each one of be assigned a number, and whatever number you're assigned, that's how many times I pick you. Right? That's what it says. That's how they're the same. Okay? Correspondence. How many times is item I in the sample? It's n numbers that add up to k. Okay? So now there's another correspondence is you want to k stars with n minus 1 bars gives an assignment to n numbers. Okay? Where the number, when you add it up, it's equal to the number of stars. Right? Because each one of these little segments corresponds to a number that's assigned to one of these n. It's going to make a number. Each one of these, it separates, each bar separates, each bar defines a number, plus you get the one at the end. Okay? So there's n plus, so the total number of positions to choose from is there's k stars and n minus 1 bars. So you have n plus k minus 1 positions in total, and you want to choose n minus 1 bars. So it's n choose n plus k minus 1, choose n minus 1. Okay? So, or there's k unordered choices from a set of n possibilities with replacement. Sample with replacement with replacement where order doesn't matter. I'm just saying all these phrases because we sort of interchange these phrases. So when you see one, just go slow. What is sample with replacement where order doesn't matter? You're picking a sample of some size, k, and you just care about which multiset you produce, not how you produce it. Okay. Okay. So the summary again. First rule is this one: k samples with replacement from n items is n to the k. Sample without replacement is n times n minus 1 times n minus 2 up to k. Second rule: when order doesn't matter, you can divide. You sample without replacement, and order doesn't matter. Then you divide out the ordering, and that's this factor of k factorial. Okay, and another way we did it is we use this. There's this idea of 1-to-1. Whenever you want to count things, if there's some other thing you know how to count, try to figure out if you can build a mapping between them, a bijection between them. Okay, and sample k times from n objects with replacement, and order doesn't matter. You only care about how often you got each item. Then that's the same as writing down a number on each item, and the number is probably 0 for most of them if k is much smaller than n. But then what you do is you think of this as stars and bars. You're picking k stars and n minus 1 bars. The n minus 1 bars are separating the stars into n groups. Okay? And you're picking n minus 1 bars. Okay? Okay, so that's... you can also think of this as another terminology thing, is k balls and n bins. That's the same thing as k samples from n possibilities. Each bin is a possibility. Placing a ball in the bin is choosing that bin. Okay? If they're indistinguishable balls, at the end of the day, all you care about is how many balls are in each bin. The bins are distinguishable. Okay, so at the end of the day, you only care the number of balls in each bin. So that says you have k balls that are throwing into n bins, so you have n numbers, the number of balls in each bin, you add them up to get k. So it's a number of ways to make n numbers that add up to get k. Okay? So if there's only one ball in each bin, that's sampling without replacement. It's pulling the bin out, and you can't throw another ball in it. So 5 balls into 10 bins, there's 5 samples from 10 possibilities with replacement. So it's also 5-digit numbers. For the first digit, you could pick any digit. The second digit, you could pick any digit, and so on. I'm assuming you can have 0 in this case. Okay, 5 indistinguishable balls into 52 bins. Only 1 ball in each bin. That's poker hands, right? 5 samples from 52 possibilities without replacement. That is poker hand, right? You're picking a subset of 52 cards of size 5. Okay, 5 indistinguishable balls into 3 bins, 5 samples from 3 possibilities with replacement and no order. Okay? And that was dividing $5 among Alice, Bob, and Eve. Okay? So these are all sort of equivalent ways of seeing it. We've seen all examples of all this. Okay. Okay, so let me give you a break. I'll give you a break. Sure.
What's with replacement and without replacement again?
With replacement means appears to be hailing. Not the best golf weather. Uh-oh. Okay, so just trying to lighten things up. I was hoping that guy would make more videos, but he seems to be busy with schoolwork. But okay, that was my video. How was it? You know, okay. So, thank you. It was. Is it like is there something called a Vine? Yeah. There's this one on fleek. Yeah, that was okay. Maybe do you know? Does on fleek mean something? It means something, right? Stylish. Yeah. Okay. So, okay, let's do some combinatorial proofs, and then we can get out of here. Okay. So n choose k equals n choose n minus k. What's the proof? You should know it. You should think about it. What is it? Is it there? Yeah. Okay, so you think about it yourself. Do you see it? Do you see the proof? Okay, let's do the proof then. Okay, the left-hand side is n choose. You can write the definition, but we're not going to do that. Okay? We hate algebra. Who hates algebra? Okay, yes. Okay, we hate algebra. We love arguments. Who loves arguments? Okay. Not arguments like you're arguing with your wife or your ex-wife, unfortunately. But well, you know, I get to play golf in the hail, so there's some compensation. Yeah, so what was I talking about? Okay, how many subsets of size k? So what we're going to do is we're going to count the number of subsets of size k. And we're not going to use algebra, right? We know that. We know the answer for the subsets of size k. Right? N choose k. Right? That's just what we've already derived this. We've done it. We beat this horse to death. Right? N choose k. Okay? How many subsets of size k? You see this? Did I make a typo? No. It's the same question. Okay, but I'm going to do it differently. Okay? I'm going to count them differently. I'm going to choose a subset of size n minus k, and then what's left out is a subset of size k. Right? Does that make sense? So the way to make a subset of size k, I'm going to make a subset of size k this way. I'm going to take my set of size n and grab n minus k of them, throw them out, and then I have k left. What is that? It's a subset of size k. So that's an equally good way of generating a subset of size k. If I throw out a different set, I get a different subset of size k. Right? So it corresponds 1-to-1 to a subset of size k. And now we know how to choose a subset of size n minus k, right? It's n choose n minus k. Okay, that's the proof you should have come up with. Okay, that's what we're looking for. Okay, not the algebra proof. Does that make sense? I mean, it turns out the algebra proof is pretty trivial in this case, but this is what is the simplest combinatorial proof you could have easily done with algebra, but it's just an argument. Okay, so remember this. What is this? It says what it is at the top, but, you know, do you remember this? Who remembers this? Pascal's triangle? Yeah. Okay, so it's a coefficient in some sense of 1 plus x to the n of this product. I mean, I guess you can argue it. I'm going to do it again later, but let's just do it quickly here. It's sort of FOIL on steroids, right? But FOIL is literally the number of terms you do when you multiply x plus y times x plus y. You multiply FOI first, outside, inside, and left. That's 4 terms. Okay, so this is going to have 2 to the n terms, right? If you think about this, what's a term? It's a term. What I mean by a term is you take one element from each of these factors and you multiply it together, and that gives you a term. So one term is 1 times 1 times 1 times 1, and that's picking 1 from every one of those. Another term might be x times 1 times 1 times 1, okay? And that's a term that looks like x, right? X times a bunch of 1s, right? But I can get x another way. How else can I get x? I could pick 1 here, and I get an x here, and then a 1 all the other places. So there's n different ways to get x. Get 1x to the 1. And this is what's happening in this triangle. Okay? Choose 1 of x, 1 or x from each factor of 1 plus x. That's the total number of terms. There's 2 choices for either choosing 1 or x. Choose 1 or x. So there's sort of 2 to the n possible, basic terms, like FOIL. If you think of FOIL as 4 basic terms, and then you collect them together. Before you collect them together, you just write them all out separately. Okay? So you simplify and you collect all the terms corresponding to x to the k. And the coefficient of x to the k, how do you get an x to the k out of these 2 to the n terms? You get an x to the k by choosing k places out of these n factors where you chose x. And the other ones you chose 1. So you get 1 times 1 times 1 times 1, a bunch of 1s, which give you 1. And then you get kx's. When you multiply together, you get an x to the k. Okay? So there's then choose k places where you can pull out an x, right? And so you have to choose those, and that's what your coefficient will be. So this triangle looks like this. It's the number of places where you choose 0 x's is 2 choose 0. This will be the coefficient of x to the 1, which is 2 terms, and you choose 1 of them. And this will be the coefficient of x to the 2. You have 2 terms, and you choose 2 of them. And this is Pascal's triangle. So Pascal's triangle, what they told you back then is this 6 here. The pattern is that the 6 is this 3 plus 3. This 4 is this 1 plus 3. And this 4 here is this 1 plus 3. Right? That's the old pattern that your whatever grade teacher told you. And so this is the pattern here. It's that this number is somehow this plus this. Right? And this number is 2 choose 1. 2 choose 1. This is 2 choose. This is 1 bigger than 2 and 1 bigger than this. Okay? So it's this equality. This is Pascal's rule. It says from this triangle you get this rule. N plus k, 1 choose k is equal to n choose k plus n choose k minus 1. Right? That's the rule from Pascal's triangle. I haven't proved it. Okay. What's your question? What? It should be 1. Oh, yeah, it should be 1. I don't know why I put 0, yeah. It's 1. 0 choose 0 is 1. Right, okay, 0 choose 0 is 1. Okay, so n plus 1. Okay, so what I'm going to do is I'm going to ask the same question twice and answer it differently. That's what a combinatorial will prove. One answer is going to be the left-hand side, and one answer is going to be the right-hand side. Okay? How many size k subsets of n plus 1 are there? N plus 1 choose k. How many size k subsets of n plus 1 are there? How many contain the first element? Okay, you take the first element. Okay, you take the first element, and now what do you're trying to choose. Wait, does this right? Okay, so I think I'm. Okay, how many contain the first element? So you choose the first element, and you need to choose k minus 1 more from the remaining n elements, right? Does that make sense? So you have your n elements. Let's just order them. And I either chose the first one or I didn't. If I do choose the first one, then I have to say how many of the sets do I have where I have the first one in it? Well, I have to have k in total, so I have to choose k minus 1 more. But I can't choose them from the first element, right, because it's a subset. So I have to choose them from n minus 1. So that gives me gives me n plus 1 minus 1. I'm choosing it from n plus 1. So it's n choose k minus 1. Right? That's this term. Okay? Now, how many don't contain the first element? Well, okay, all the sets that don't contain the first element, you don't pick the first element, right? So you're picking only out of, instead of n plus 1 items, you're picking out of n items, right? And so you're picking how many from n items? K of them. So that's n choose k. You need to choose k elements from the remaining n elements, right? You can't choose from the first element anymore. You can't choose the first element anymore. Okay? And so that's n choose k. So n choose k minus 1 plus n choose k. So now this is the left-hand side. This is the right-hand side. Okay, I switched everything. Okay? Does that make sense? So it's a combinatorial proof. Like, you can do this with algebra, right? You can actually write out the expressions and multiply and get a common denominator and do all of that if you want. Okay, but this is a different, right? We're saying don't do that, right? Just make an argument. Yeah.
If you were to do that, that's the binomial expansion.
It's Pascal's triangle, yeah. It is. It's what we saw in the last slide. Okay. Okay, so this is how you can prove it, and right, we did no algebra, right? This is really kind of nice. Okay. Okay, so here's another one. Okay, so how might we prove that one? We know how to count the left-hand side, right? Everybody knows what we're going to do on one side, right? The left-hand side is just the k subsets of size k of n. Okay. Okay, so now the right-hand side, we're also going to count the subsets of size k of these n items. And we're going to do what we did on the last slide kind of a lot more aggressively. We're going to keep going. Okay? So we're going to say, let's think of our elements and order them. Okay? And what we're saying here, consider size k subset where I is the first element chosen. So we order all our elements, 1 through n, and we say, let's think about different kinds of subsets. Some subsets might have the first element. Okay? But let's just look at, whatever the subset is, let's just look at what its first element is. And if it's I, we're going to count those. Okay? So for any subset where I is the first element, can we pick any of these? I is the first element of this subset. I have some subset. I is the first element. Can we pick any of these elements in that subset? No. Right? Does that make sense? So, and we know we picked I. So we know I is one of the elements in our subset, right? And we know we can only pick from here, from these other n minus I elements. Okay? So we have to choose k minus I elements from here, from these n minus I remaining elements, the underlined elements. Right? Okay, so if you consider any subset of size k, again, the combinatorial arguments are short, but you really have to understand every piece of them. Okay? So we're going to think about a subset of size k where I is the first element chosen, and how many are there? Okay? So I know each one of those has I as its first element, and then it has k minus 1 more elements from all these elements which are bigger, and there's n minus I of those. Okay? So that's n minus I, choose k minus 1 such subsets. Okay, you add them up, you get the right-hand side. Okay, it's a total number of sizes of subsets of size k. Okay, and the number is also n choose k, which is the left-hand side. Okay, so I counted the number of subsets of size k twice in two different ways. One way I just said n choose k because that's what we know. On the other way I said let's organize them in this fashion. And what do I get out of it? I get this this quality, right? I get this identity. So it's a way to derive identities without doing some. Now the algebra would be like even more horrible, right? To do such a thing. Okay, 2 to the n is n choose n plus this one. We sort of saw this before. I like to do the same thing several times, so that's good. That's fine. How many subsets of 1 through n? So we're going to, again, count this object in two different ways. So you can construct a subset with a sequence of n choices. For example, we did this way when we did countability, right? When we did the diagonalization proof of the power set. For each subset of the integers, for each integer, we just write down a 0 or 1, depending on whether it's in the subset. That's what the notes does. Okay? So if element is either in the subset or it isn't, so there's two possibilities, and there's n elements to decide whether they're in the subset or not. And if you make one of the choices, that distinguishes it. All those choices give you a unique object. So it's 2 to the n subsets. Now, how many subsets of 1 through n are there? Well, there's n choose I ways to choose I elements of 1 through n. And then you sum over I to get all the possibilities, right? Every subset has some size, so you sum over all of them. And they're disjoint sets. Why are they disjoint? Why can we sum over these sets? Because an I element subset is never an I plus 1 element subset, right? An I element subset is an I element subset. So there's no overlap. Nobody's in more than one set. So these are disjoint sets. Okay? Which is also 2 to the n. Okay? So it says we counted them this way, we got 2 to the n. We counted them this way, we got this expression. So these expressions are equal. Okay. Okay, so here's another proof. I think. Okay, so this is just a proof of this binomial theorem. So I was just going to show you that, in fact, when you take this exponent, you get these coefficients, right? Okay. So I showed you that 2 to the n is equal to this thing too, right? Do these things look similar to these things? Sort of same objects, right? But okay. Okay, so it's true for x plus y to the 1, right? This is the base case. I'm going to use induction. Okay. So x plus y to the n is the same as x plus y times x plus y to the n minus 1, right? And then you can use a distributive property. And you get x to the plus y to the n is equal to x times x plus y to the n minus 1 plus y to the x plus y to the n minus 1. Right? Okay. Okay? Okay. So x plus y to the n minus 1 has, what we're doing is we're counting these terms. We're saying the number of terms that look like x to the n minus 1 to the y times y is n choose 1. Okay? So we're trying to prove that it's n here it would be n minus 1 choose k is the number of terms in this expansion who look like this: x to the n minus 1 minus k times y to the k. Okay? I'm just using the induction hypothesis. Okay? And the first term, so this is the first term here. Now when you multiply a term that looks like this by x, you get x to the n minus k times y times y to the k. Right? Because there's just a minus 1 here. When you multiply by x, when you multiply this thing by x, you get x to the n minus k times y to the k. So n minus 1 choose, and now of this form, it's also, you can use it inductively. You can say, well, it's a total number minus this thing, so that you do n minus 1 choose k minus 1. So that's what you get here. And they have this form. And now, which is, when you simplify this, n minus 1 minus k minus 1, which is n minus k. So now in the second term, you're multiplying by y. So the second term gives you that all the terms that look like this are multiplied by y, so they go from x to the n minus k times y to the k minus 1 to n minus x to the n minus k times y to the k. You just add 1 to the exponent there. Okay? So what this says is that n minus 1 choose k minus 1 plus n minus 1 choose k. We know from before that is n choose k. Okay? So there's n choose k terms of this form. Okay? So this is a proof of this sort of the big binomial theorem. Okay? So again, just counting, this is just using induction. And we're again using this combinatorial fact, which we proved before. It's Pascal's triangle. Okay? So now let's prove this theorem. Didn't we just prove this theorem on the previous slide? 2 to the n equals n choose, right? Okay, so let's see how we can prove it again. Now you can just plug in 1 and 1 here. And what do all these terms become? What is 1 to the n minus 1? 1, right? Okay. Okay, so, right? So if you plug in 1 plus 1, what do you get over here? You get 2 to the n. And now x and y are 1, so x to the n is 1. X to the n minus 1 is 1, and y to the 1 is 1. So you get this n, choose 1, and so on. Okay, so it's another way to prove the statement we proved on the previous slide. Okay. Okay. Oh, yeah. This lecture is a little short today. Sorry, because we're going to move to probability, and we didn't want to split the lecture. But let me just review it real quick, and then you guys have a. I'm going to give you your time back. Okay. So inclusion exclusion is a union bound is too much. What's the idea here? Again, I'm not going to summarize. I'm going to tell you. I'm going to sort of summarize by telling you the ideas we use to make the arguments, right? Because that's what we're trying to teach. Okay? So the union bound is too much. The union bound is add up the sizes of all the sets. That's overcounting, right? Because some element may be in 2 sets, right? We're going to do every argument a few times, right? So now, when you do the union bound, what you've done is you counted any element that's in more than one set too many times. Okay? So you subtract those. You subtract all the elements that are in 2 sets in some sense. You subtract all the overlaps of elements, of sets. Okay? But those in 3 sets, they were added 3 times because the first time you added them once for the one set, once for the other set, and once for the other set. So you added them 3 times. But those things in 3 sets were also in 2 sets 3 times. Okay? So they were subtracted 3 times, right? This element that's in 3 sets, say it's an A, B, and C, it's also an A intersect B, B intersect C, and A intersect B. So when you subtracted it 3 times. So you need to add it back. Right? You need to add the size of all the sets with all the intersections of 3. Okay? And so on. You can continue. That is what the argument is for the general inclusion exclusion. Okay, so now there's this case samples from n items with replacement without order. This was a mess, right? We couldn't use the second rule of counting and divide out all the orderings. Because sometimes you might have picked the first item 5 times, and other times you pick all different items. So when you divide out all different items, you divide out a lot more than if you have the same items 5 times. Okay? So what we did here is we mapped to k stars and n minus 1 bar diagrams. And those bars and stars, and you just picture them in your head. You should see that every bar gives you a number to the left. And you get an extra number to the right. So you get n numbers from the bars. And now those numbers have to add up to k because there's k stars. That's what you're counting. That's how you're getting your numbers. Okay? So you count the star and bar diagrams, which is easy. It's just you can use choose again. Okay, and then finally we did combinatorial proofs. And what's the idea there? You count the same thing in 2 ways to get a valid equality, right? And what's the first one we saw in this class? The sum of the degrees is twice the number of edges. Remember that in graph theory? That may not even be the first one we saw. So we've done this before. We've done math by counting the same thing in 2 different ways and getting 2 different expressions. Those expressions must be equal. Okay? Each subset either has or doesn't have an element. That's 2 to the n. Each subset has a size I. So now you just sum over all the sizes of the number of subsets of that size. Okay? Okay, that's good. Okay, so we'll see you in office hours. So, if you ever come, yeah.